Swayam Prabha. Digital India. Educated India.
Welcome to lecture 18, the NPTEL online certification course on bioreactors. We will begin module 5 today, which is the last module of this course. The title of this module is the cell view of a bioreactor. We have always maintained that the cells are the actual factories that produce the product in the bioreactor. They could be products themselves. Now, if you recall module 2, the title was two major outcomes of a bioreactor: the cells themselves, or what is known as the biomass, or the products that are made by cells or through enzyme reactions. So, we are going to look closer into what is happening, or look into what is happening inside these cells in a bioreactor, and how we could use some of those to make bioreactors perform better. Just to repeat that, the cells are the actual factories in a bioreactor, and any significant improvement needs to happen at the cell level, because that's the more fundamental level. Understanding anything from a fundamental level is always much better for guaranteed improvement, and that is what we are trying to do here. We will look at some approaches that target the cells in the bioreactor. In fact, I have a theme for this. We will first look at the cell as a black box, these stoichiometry aspects, black box, what is happening, what we could do. Then we will open a window into that black box and through the indicators of status of the cell. The status is quote unquote. There are many statuses that are talked about. We will look at some aspects of that. Then we look inside through the window. Maybe from other directions also, maybe we'll open up some doors also and look inside. And an example of that is metabolic flux analysis, and then try to modify things according to our needs, such as DNA modification, use of recombinant DNA technologies, and so on and so forth. We will just barely touch upon them because that's an entire field in itself, recombinant DNA technology. I will just talk about its relevance to improving the operation or the outcomes from a bioreactor. So that's going to be the theme of this particular module. First, the bioreaction stoichiometry, which we will cover in this lecture. Then let us look at a problem. Then in the next lecture we will solve the problem and then go forward. Bioreaction stoichiometry. The term stoichiometry, it is used heavily in chemistry. It is also used in engineering. In engineering, it actually denotes the material and energy balances, or things that are based on the mass conservation principle and the energy conservation principle. That is what is called stoichiometry in some fuzzy fashion in engineering. You have books on stoichiometry. Similarly, bioreaction stoichiometry refers to material and energy balance calculations that involve biosystems. Bioreaction stoichiometry helps us make educated guesses when the complete data is unavailable. That's how we are going to look at it. We just started looking into the cell at the cell level. We had led to this in our earlier discussions, but this is where we are actually getting to look into the cell. And the first approach is that the cell is a black box, and what we can gather from whatever we observe it as a black box, but with the thinking that there are things going on inside the cell. A very useful concept for the use of stoichiometry is what is called the degree of reductance. This is a formulation which makes bioreaction stoichiometric calculations easier, and it is denoted by the capital Greek symbol gamma, as is given here. You see here, this is the degree of reductance. We have degree of reductance given for each substance. As a first approximation, it can be understood as the number of electrons that a substance can donate. So it's reasonably fundamental, a fundamental concept. It works at the electron level, electrons are conserved, and so you can do things there. So it is understood as the number of electrons that a substance can donate. This is only as a first approximation. This is not always valid. Okay, so it is more of a number that is assigned to a certain molecule. We'll see this. Thus, the number of electrons that oxygen can donate is -4. Okay, and O2 is -4, O is -2, carbon is +4, and nitrogen is -3. It is the number of electrons that a substance can donate. And let us complete this and then come back to this particular aspect. Gamma of phosphorus is +5, gamma of sulfur is +6, gamma of CO2, this is +4C, this is -4O2. So we can just add the degree of reductances and arrive at the degree of reductance of a compound that is made up of these elements. So this is 0, and similarly H2O would turn out to be 0 here, because hydrogen is 1 and oxygen is -2. You have 2 of hydrogens and 1 of oxygen. That turns out to be 0. So the basic things are O, C, N, P, and S, and from that you can get oxygen, nitrogen, CO2, H2O, oxygen, CO2, H2O, and so on and so forth. Okay. So the negative value actually implies that the substance can accept electrons instead of donating them, and this is understood as the number of electrons that a substance can donate. That is the degree of reductance. Let us see what we can do with this concept. Before that, as was briefly mentioned earlier, the degree of reductance of any substance can be obtained by the algebraic addition of the degrees of reductance of its constituent elements. For example, even for a complex molecule such as a substrate, we had earlier looked at O2, H2O, CO2. Even if you have something like a carbohydrate here, CHAOB, the degree of reductance of the substrate is the degree of reductance of its constituent elements added together. Therefore, this says 1 carbon, 4 into 1, the degree of reductance of carbon is 4, therefore 4 into 1, plus the degree of reductance of hydrogen is 1, it has A atoms of hydrogen, so 1 into A, and the degree of reductance of O is -2, and the number of atoms is B, so -2 into B. So that will turn out to be whatever it is, 4 plus A minus 2B. And you can also think of a degree of reductance for cells. It is indicated as gamma X, and let us say that the cellular composition, people have determined cellular compositions. There are tables in one of your textbooks, Bailey and others, which is from another paper actually, which gives you the compositions of the elemental compositions of various cells, and you'll find this to be approximately okay. The representative formula, chemical formula for cells is C, H, A, N, B, and OC predominantly. So the degree of reductance of cells, or gamma X, would be 4 into 1 for carbon plus A into 1 for 1 into A for hydrogen plus -3 for N into B, and plus -2 for O into C. So this would be the degree of reductance of the cells. This gamma X has been found to be about 4.2 for a wide variety of cells, and herein lies the strength of this method. This has been estimated, and similarly the parameters that we are going to look at chiefly, the chief parameters have been estimated for a wide variety of substances. These happen to fall within a very narrow range. And therefore, if you take the average value of that range as a representative value, we can do first level calculations very easily and get insights into what is happening, which can in turn be used to improve the bioreactor performance. Therefore, in the absence of actual data, gamma of x equals 4.2 is a good first approximation. Let us look at the application of this, a couple of applications, then I will assign a problem. Let us consider a typical cell and product formation. This is a stoichiometric equation that represents the cell and product formation, starting with a substrate, carbohydrate CHMOL, and ammonia. Both these are substrates. This is the nitrogen source here. So carbohydrate CHMOL plus A, this is the stoichiometric coefficient of NH3 plus B of O2, oxygen is of course required, gives you a certain Yx, which is the stoichiometric coefficient of cells. I think, yeah, this is the substrate, this is the cells, CHP, ON and NQ, and plus Yp, which is the stoichiometric coefficient of the product, CHR, OS and T, that's the product, plus water, C molecules of water, and D stoichiometric coefficient of CO2. So this equation, stoichiometric equation, represents the cell and the product formation in a reasonably general format. We will choose this as the equation for our analysis of a few things that we will do in this lecture. Electrons we know are conserved, right? So by that principle, the number of electrons need to be conserved. That's what we just mentioned. So if you count the number of electrons on this side, that must equal the number of electrons on this side. How do we count the number of electrons? We have degree of reductance. Okay, that's how the degree of reductance thing ties in. So gamma of S, the substrate, plus the gamma of ammonia into A, because that's a stoichiometric coefficient here, A times minus 3 for N plus 3 for hydrogen, plus B times minus 4. I am writing this as an equation, therefore I am bringing all these to the other side, minus Yx gamma x minus Yp gamma p minus C times H2O was 0, so that is 0, minus D times CO2, gamma of CO2, that is 0, that equals 0. So ammonia drops out, water drops out, CO2 drops out, and we have the remaining things. Therefore, this B, A is already dropped out, C has dropped out, D has dropped out. B is the one that remains. B is nothing but 1/4 of, by appropriately transposing this equation, all these would become pluses, this would become minus 1, and this is multiplied by a factor of 4, minus 4, so that when taken to the other side would be gamma S minus Yx gamma x minus Yp gamma p divided by 4. So that is B. So you could write this as, multiply again, 4B by gamma S plus Yx gamma y by gamma S, right? What we are doing is, we have multiplied this by 4 and then we are dividing throughout by gamma S. So 4B by gamma S plus Yx gamma x by gamma S plus Yp gamma p by gamma S, that equals 1. Okay, this is a powerful expression. This indicates the fraction of the available electrons from the substrate that has been transferred to oxygen, because B is the stoichiometric coefficient of oxygen, 4B is the number of electrons that is associated with, and so on. So 4B by gamma S gives us the fraction of available electrons transferred to oxygen. Yx gamma S by gamma S gives us the fraction of available electrons transferred to cells. Similarly, Yp gamma p by gamma S gives us a fraction of available electrons transferred to the product. all these add up to 1. These are all fractions, so they should add up to 1. There are some special symbols that we use for each of these. The fraction of available electrons transferred to oxygen is represented by epsilon. The fraction of available electrons transferred to cells is represented by eta. The fraction of available electrons transferred to the product is psi. So epsilon plus eta plus psi is 1. So this is something that we can use. Now using these, let me show you how to estimate the heat that is generated from the cells in the bioreactor during growth. It is known, I said the power of this method comes because the rules of thumb values are known, right? So it is known that 27 kilocalories of heat are generated per mole of available electrons transferred to oxygen. That epsilon, the fraction of available electrons transferred to oxygen. For every mole of electron transferred to oxygen, 27 kilocalories of heat are generated. This is known. In our example, the equivalence of available electrons transferred to oxygen is 4b. Therefore, the heat generated is 27 times 4b kilocalories. From another angle, if the rate of oxygen consumption, say QO2 in moles per gram cell, is measured using a DO probe, if you process the DO data, you can get the oxygen consumption rate. The rate at which heat is generated can be estimated. Then it becomes powerful. Okay, once we know how much of heat is metabolically generated, we can a priori say what kind of a cooling design we need to look at. That's rather powerful. This will help us design cooling coils for obtaining the desired rate of cooling. If it's cooling, it's okay. You can use a coil because the temperature is not going to go down too much. It's not going to affect the cells. Whereas heating coils are not really used. Use a jacketed system. Similarly, a jacketed system can also be used for cooling, but cooling coils are also used. So the rate at which electron is transferred to oxygen is 4 times QO2 x into V. Each oxygen corresponds to 4 electrons. This is the oxygen uptake rate in moles per gram cell. We need to multiply it by the cell concentration to get it in appropriate units, and then multiply it by the bioreactor volume to get it in the units that we need. So this is the rate at which electrons are transferred to oxygen, number of electrons per unit time. Right? So if that is the case, the rate of heat generation for each mole, it is 27 times 4b. So in this case, for each mole it is 27 kilocalories. So in this case, it is 27 times 4 QO2 x V. This gives you the rate of heat generation, an estimate of the rate of heat generation, which can be helpful for us to make many decisions. So this is based on what is happening at the cell level. Now let me assign this problem, and we can finish up this lecture here. When we come back, we will solve the problem in the next lecture. The practice problem 5.1 reads as, let us consider the same stoichiometry as earlier. It's reasonably general as long as ammonia is used as a nitrogen source and some carbohydrate is used as a carbon source, and it's aerobic. This is reasonably general. So CHMOL plus ANH3 plus BO2 giving you YX, CHPON and Q plus YPCHROS and T plus CH2O plus DCO2. Estimate the cell oxygen yield coefficient YX/O, defined as the amount of cells produced to the per amount of oxygen consumed. And this we need to find out in terms of the relevant ones among gamma X, gamma S, gamma P, or epsilon, eta, nu. Right? In terms of these, if we find, we have estimates of all these. Gamma X we know is 4.2. gamma S, gamma P can easily be calculated. Epsilon, eta, new values, some estimates, some ranges are known, and therefore we can estimate the cell oxygen yield coefficient. And while doing this, assume that the biomass fraction of carbon in cells is 0.5. So you can say that the cells are growing aerobically, so you get a fraction of 0.5. It's anaerobically, it's around 0.1 or so. Okay then, see you in the next lecture when we solve this problem, and then we go ahead.